Hello everybody, my name is Paul Dobson and I'm a postdoc at TU Delft. I'll just start by thanking all the organisers for putting on this virtual conference and for giving me the opportunity to speak today. What I want to talk about today is infinite dimensional, piecewise deterministic Markov processes. This is based on joint work that I've done with my supervisor, Joris Berkens, and Andrew Duncan and Michaela Rotova. The structure of today's talk, I'm going to start off by talking about a general introduction, why we care about trying to construct these processes in infinite dimensions, what the challenges that we might face in general, and how we could think about resolving some of those. I'm going to concentrate for the entirety of the talk on how we construct these processes and proving well-posedness for them, and only briefly discuss about any other properties we can show. After the introduction, I'm going to move on to talking about two specific examples. First of all, how we can construct a version of a zigzag sampler in infinite dimensions. And then finally, I'm going to talk about a process called the Boomerang Sampler, which differs from a zigzag sampler in the choice of the reflections that we might use, but also because this has non-linear paths, whereas the zigzag only has linear paths. And as we will see later on, Boomerang Sampler has some properties, in particular this non-linear paths, that enable us to have a bit of a richer analytic structure in infinite dimensions. So to begin, why do we care about constructing these processes in infinite dimensions? Well, the first point to that is there are many examples that are interesting in their own right, but that are infinite dimensional, such as trying to do an inverse PDE problem. So for example, we have some elliptic PDE of which we can obtain solutions to this PDE. We're interested in finding out, say, the diffusion coefficient or some other properties about the PDE. So this diffusion coefficient is some function, so therefore it lies in an infinite dimensional space. So this problem is fundamentally an infinite dimensional problem. Similarly for diffusion bridges. So say we have a series of points, time points, and we want to construct the process between these time points. Then we need to construct some path. So our process is going to be living in path space. Again, so this is going to be an infinite dimensional problem. And many more examples can be found in the notes by Stuart in 2010. Reverse way of looking at this is, there's always a great deal of talk about how we can do sampling in high dimensional spaces. And if we can understand what processes work well in infinite dimensions and what properties these processes have in infinite dimensions, this can give us an insight into what happens for very high dimensional problems and what processes might work well and which ones may not. So, what's the problem? Let's start off with letting H just be a separable Hilbert space, and as in any MCMC situation, we want to sample from a given measure. Immediately we have to be quite careful here, because I've just written down what we would normally write down in a finite dimensional setting. But of course Lebesgue measure does not exist in infinite dimensions. So instead of using Lebesgue measure as our reference measure, we shall instead introduce some other measure, pi naught, which throughout this talk we're just going to take to be a Gaussian measure. Now I wanted to highlight this immediate difficulty we have when going to infinite dimensions, because this influences what sort of processes we may wish to use. In particular, if we look at these typical PDMPs that we use in finite dimensions, we often use processes like the zigzag sampler or the bouncy particle sampler, both of which have linear dynamics. So these are dynamics which preserve the Lebesgue measure, but will not leave pi naught invariant, will not preserve the Gaussian measure. Whereas the Boomerang Sampler, which has nonlinear paths, and which I'll explain later on, this has circular paths, which will in fact preserve the Gaussian measure. This is one of the reasons why working with the Boomerang Sampler in infinite dimensions turns out to be a bit easier. So now, there are other infinite dimensional Monte Carlo algorithms out there, In fact, many of the regular finite dimensional algorithms have some sort of infinite dimensional counterpart. From Metropolis Hastings, Random Walk Metropolis, Langevin, and Hybrid Monte Carlo, and I've given a selection of papers for each of these topics. And I also want to distinguish between the first four and second order Langevin HMC, because the first four are all reversible algorithms, and the last one is an irreversible algorithm. And part of the desire to understand PDMPs in general, because they allow us to have irreversible sampling algorithms. But also the difference between using an infinite dimensional hybrid Monte Carlo and using a second order Langevin HMC algorithm is again this difference of using linear paths that appear in the hybrid Monte Carlo to using circular paths which appear in the second order Langevin HMC, which is a HMC analog to this difference I was talking about between using the linear paths in the zigzag process and the circular paths that we will see in the Boomerang Sampler. So how do we construct an infinite dimensional PDMP? Well, what do we need to construct a PDMP? First of all, we need deterministic dynamics. So in infinite dimensions, this is some semigroup with a generator A. For this talk, this will either be linear dynamics, as we talk about with zigzag and bouncy, or some sort of Hamiltonian flow, like the circular dynamics that we'll see for the Boomerang Sampler. We need an idea of sort of a reflection operator. So this is some probability kernel that defines how we reflect, and a rate lambda, which tells us when we're going to reflect. Throughout this talk, we're going to assume that our reflections are norm preserving. So whenever we reflect, the norm is always less than or equal to the norm of where we started. So examples of reflections that have this property are taking, let's say, we've got our space split into space and velocity, and if we just reflect the velocity from v to minus v, then this is norm preserving. If we take a zigzag type operator, where each reflection composed of picking a direction and changing the sign of just that direction, then this will also preserve the norm. But as I'll discuss a bit later on, this will cause us problems if we want to talk about a bouncy particle sampler type reflections. The third type of operation we need is refreshments. So again, this is some probability kernel Q and a rate lambda. We're going to assume that for each initial condition, for each point Z, wherever we refresh to, we can bound uniformly. I hope this isn't too surprising of an assumption for refreshments. And then we can summarize this process by our linear dynamics, AZ, our reflections, and our refreshments. And this is the framework that we're going to try and use to construct our PDMPs in infinite dimensions. The question is, what can go wrong? Well, let's define Ti to be the ith jump, so either a reflection or a refreshment, and we're just going to define T-explode to be the last jump. Our process is non-explosive if T-explode equals infinity. Or to put that another way, our process explodes if we can have an infinite number of jumps in a finite amount of time. So it's clear that this is not possible if our rates, lambda refreshment and lambda reflections, are both bounded. However, we're not going to assume that. We will assume that our refreshment rate is bounded, so we only have problems about reflections. And to keep things fairly concrete for this talk, I'm going to assume that this operator A, So this is defining our deterministic dynamics. And you assume this is globally Lipschitz, so we have plenty of bounds on our deterministic dynamics. And I'm going to assume that reflection rate is bounded on bounded sets. And under these assumptions, and the assumptions that we listed on the previous slide, we can actually show that our process is non-explosive. So what happens is our process is always bounded except for refreshments, and refreshments we can control because the rate of refreshments is bounded. But the main problem for us with this setup is, as I indicated on the previous slide, that we would like to weaken our assumptions on reflections. Because, again, as we will discuss later on, this assumption is not satisfied for all the conditions, for all the examples we'd like to consider, and in particular if we want to try and get an infinite dimensional bouncy particle sampler, this assumption gives us problems. So this is the general setup of how we get well-postedness in infinite dimensions. Now I want to talk about how this theory fits for the zigzag sampler. First of all, what is the infinite dimensional zigzag sampler? Let's recall we're trying to sample from this measure pi, and we're going to do it by introducing a velocity variable. So we're now living on the space h times h, and we've got to decide what measure we wish to sample on the new variable, the velocity variable. So in finite dimensions, the zigzag sampler has reflections by just flipping the nth component. So we're going to do exactly the same thing in infinite dimensions, except now we have an infinite choice of components. So we're going to let En be just an orthonormal basis for h, and we're going to just flip. The nth flip is just flipping the nth component with respect to this basis. So the zigzag process is now defined by, for our linear dynamics, they just move at a constant speed v in the direction x, and we have an infinite choice of possible reflections, and each reflection just composed of flipping the nth velocity component, and then we're going to include refreshments. Okay, so does this satisfy the assumptions we said at the start? Well, in this case, reflections preserve the norm, so they're not causing us any problems. Except, what is lambda n? What are our reflection rates? Well, let's make this a bit more concrete. We're going to take pi to be Gaussian, mean 0, and covariance operator sigma. I'm going to assume that En are the eigenvectors of sigma. In that case, we can write down what we need to take the reflection rate to be. Well, it's exactly this. We take the maximum with 0 of the inner product between Vn and the nth derivative of u. So this ensures that we target the e to the minus u part of our measure. But we also need to compensate for our Gaussian measure by adding on Vn gamma n to the inverse to the minus 1. Now, gamma n are the eigenvalues of sigma. But this is a problem, because in order to have well-posedness, we need that the sum of all of these is well defined, which is to say the rate at which we have a single reflection, our first reflection, has to have a finite rate. Otherwise we're having our jump immediately. And if we're having jumps immediately, obviously we're going to have, or we can expect that we're going to have an infinite number of jumps, a finite amount of time. Now, even if u equals 0, this causes us problems, because for a generic v in our Hilbert space, we don't know that Vn gamma n inverse sums up. In fact, remember that sigma is of trace class, so the sum of gamma n is finite. So in fact, gamma n is tending to 0, gamma n inverse tending to infinity. So we need to only look at V for which this sum, the sum of V and gamma n to the minus 1, is finite. And to do that, we're just going to choose this stationary measure for the velocity so that it has full support on this condition. So the set of V which satisfy this is measure 1 with respect to nu naught. How can we achieve this? Well, we can just pick a single sequence, A, which satisfies this condition. So just take A to have sufficient decay in its tails to ensure that A lies in the set of such that its inner product with gamma is finite. And then we just set nu naught to be the measure which on each component, so the nth component is an times a random variable psi n, which takes values plus and minus 1 with equal probability. So in effect this is an infinite dimensional version of the uniform measure on plus or minus 1 to the d, which is the invariant measure for the velocity of a finite dimensional zigzag process, except we've had to weight each of our components by this vector an to ensure that we have sufficient summability to define our rate lambda. Another way to view this is that what we're requiring here is that the velocity is in some sense a much smoother space than the position variable. So as I say, we can do this, but we require a certain amount of care to handle this problem. And to get more properties, we're going to have to be keeping track of what's the smoothness of the velocity that we require in comparison to the smoothness of the position. And I want to compare that with the Boomerang Sampler. So let's introduce the Boomerang Sampler and see why this is a bit easier to work with. So the Boomerang Sampler is given by this generator. So if we compare this to the zigzag sampler, our reflections, in this case, are defined by the exact same thing. Our nth reflection is we take the nth component of the velocity and we just change the sign. And our refreshment is exactly the same. But what we've changed is the deterministic dynamics. So where previously we only had the inner product between V and the space derivative, we now also have this extra term of minus x times the velocity derivative of f. So that is that the deterministic dynamics are corresponding to this ODE at the bottom of the side, x dot equals v and v dot equals minus x, which is to say that the deterministic dynamics are just running in a circle. Now this process is called the factorized Boomerang Sampler and was introduced in June, just gone, by Perkins, Grassi, Kamati, and Roberts. But what's useful for our purposes with this process is the fact that these deterministic dynamics preserve the Gaussian measure. And as we will see, this gives us a simpler form of the reflection rate, which is what gave us the problem in the zigzag case, and in general will allow us for a bit of a cleaner analysis. So what is the reflection rate in this case? Well, the reflection rate now is just the maximum between Vn and the nth derivative of u. So there is no more of this Vn times gamma to the minus 1, because we don't need to compensate for the Gaussian measure, since our deterministic dynamics already preserve the Gaussian measure, which is to say if we were to have absolutely no reflections, then we would already have the Gaussian measure as our invariant measure. And just to give a hint of what more we can say about this, now that we've got well-posedness and this slightly cleaner reflection rate, we can use the theory of hypercoercivity to prove an L2 convergence to equilibria exponentially fast. And using this exponential convergence, we can actually prove convergence of a finite dimensional version of this process to this process, where the convergence happens uniform in time. Now I just want to finish by discussing a different form of reflections that we can take. And so this was also introduced in June as a different version of the Boomerang Sampler, which is to use contour reflections. So that is, we define a reflection operator, V, R, which acts on V by just reflecting off the contours of the derivative of U. If one was to just take sigma to be the identity, then we should recognize this as being exactly the reflections that appear in a bouncy particle sampler. However, again, because we've got to preserve the Gaussian measure now, we need to weight these derivatives by sigma. Now this isn't a problem in the finite dimensional setting, because we can find an alternative norm which this preserves. Namely, it preserves the Cameron-Martin norm. Now, in finite dimensions, Cameron-Martin norm is equivalent to the original norm, so this doesn't give us any problems. However, in infinite dimensions, this Cameron-Martin space has zero measure, so this isn't helpful anymore for us. And we would really like to be able to understand what happens when we use this type of reflections, because this not only will allow us to discuss contour reflections for the Boomerang Sampler, but this would be a stepping stone and a big step towards understanding how an infinite dimensional bouncy particle sampler would behave. But at the moment we just don't know how this works. So just to summarise what we've discussed today, to talk about how we can construct PDMBs in infinite dimensions, under what assumptions we have non-explosivity. We've discussed how these conditions are satisfied by two different types of processes, the zigzag process and the Boomerang Sampler. We found that we required this idea of smoothing the velocity to ensure that the zigzag process exists. And we didn't need that when we had the circular dynamics of the Boomerang Sampler. And this allowed us to have more straightforward, to be able to get more analytical results for the Boomerang. Still many questions that we haven't addressed, like how does the performance of these two samplers actually compare? Boomerang Sampler was nice from the analytical point of view, but does it actually perform better? And can we mimic some of these results, the hypercoercivity that we got for the Boomerang, for the zigzag process, and just keep track of all this extra smoothness that we need to worry about? We have these different choices of reflections, contour reflections, the sending the velocity to minus the velocity, or the zigzag type reflections. Is there any way of deciding which one of these is better in some sense? Finally, as I mentioned at the end, can we try and find a way to fit the bouncy particle sampler into this framework and get some understanding for, does this process exist, and if it does, what are its properties, and if it doesn't, what goes wrong? So thank you for listening.